In this video, I will explain the stepwise selection method. So what is stepwise selection method? I will explain the forward stepwise selection only, but the backward stepwise selection also can be defined analogously. Stepwise selection method as follows. The first, you test the case p equal to 0, which means you will just have the parameter beta 0 and then minimize your RSS value by controlling the beta 0 parameter for your entire training data point. So essentially it becomes yi minus beta 0 square. So yeah, in that case beta 0 is just some empirical average of your yi. And the second step, you consider all the case p equal to 1. So in this case, you have two parameters, beta 0 and beta 1, right? And also, you have p different case. You can choose the first predictors. You can choose first predictor, you can choose the second predictor, up to you can choose p's predictor. So for the p different case, you train your model with parameter beta 0 and beta 1 and minimize the RSS value yi minus beta 0 minus beta 1 x k xik square. So here k can be from 1 to p. Okay, so among p different model, we will choose the best one. What is the best one? The best one means the model that minimizes the RSS value. Since all p different models share the same size, they all have two parameters. So this comparison is very fair. So we just need to find the algorithm that has the minimum training error. Okay, so let's say S1 star is the set consists of the best predictor. Okay, let's say this is P1. Okay. The third step is we will consider case P is equal to 2. So we will consider case when there are two input predictor. So in that case, we have three parameters, beta 0, beta 1, and beta 2. But in that case, we will keep the P1, the best input predictor in the previous step, and then we just add one more predictor to the set, which means we will consider set as, which of course the subset of entire predictor, and the size is equal to 2. So we will choose two input predictor among p different input predictor, but S also must include the first subset, S1 star. Okay, that is the condition for the third stage. And then among the S that satisfy all these three conditions, we will find the parameter beta 0, beta 1, beta 2 that minimize the RSS value yi minus beta 0 minus beta 1 xi p1 minus beta 2 xi k square. So here k can be from 1 to p except the P1, right? The input predictor which already selected from the previous stage. And then compare P-1 models, right? And then find the best model that minimizes the RSS value. Again, since every model shares the same number of parameters, all models will use beta 0, beta 1, and beta 2, 3 different parameters. So this comparison again very fair. So we will just need to look at the training error and then find the best model that has the minimum training error. Okay, so we will continue this process again and again and again up to the stage P+1, right? At the stage P+1, in the end we will have the full subset, and we can find the RSS value for the full subset. Okay, so there are two remarks. First one, as the stage goes on, we will see the lower RSS value. Essentially, since we increase the one's more parameter at each stage, we basically have one more degree of freedom, so we can minimize, we can decrease the RSS value compared to the previous stage. So when you plot the RSS value, and this is stage number, you always see monotonically decreasing, right? So the RSS value is not good predictor or good metric to decide which stage is the best. Okay, so in the previous description, at each stage we find the best subset among the same size of subset. But in the end, we have to provide one single model. So we have to decide which stage is the best for making the best test error. Okay, so when you use RSS value for that kind of selection, you always choose the last stage, but this is not good, right? The last stage generally have more parameters, usually have more chance to be overfitted. So this is not good news for test error. So we have to design more smart selection rule that can consider both the number of parameters or number of predictors and also the RSS value. Okay, so this is the first remark. And also the second remark is let's say as K star is the best subset at the stage K, or the size K. Usually the SK star is not equal to argument set that has set size K summation mean beta 0 beta K RSS value with parameter beta and set S, input predictor S. So which means SK star is not the best subset with size K that minimize RSS value. Why? So in the previous stepwise selection method, we reused the K-1 selection which was obtained from the previous stage. Okay, but when you consider set size K, maybe the previous k-1 selection are not good. Okay, maybe the k-1 selection, the prediction, input predictors can be coupled with all remaining ones. So all the remaining input predictors are very redundant. Maybe if you remove some of input predictors you already selected before and then add another ones, then you can design more orthogonal information, more independent information, and then you can get better RSS value. Okay, so one by one incremental selection not always guarantee very nice performance. So this is called greedy selection. So every time you just see the one element increment and then choose the best one, that the marginal increase is the best among one more addition. This is very greedy approach, so that is not optimal. To find the optimal, the real best subset of which size equal to k, you have to consider all set size k, all subset having size k, and then you have to compare every subset having size k. But the problem of this process, considering every possible subset having size k, is the algorithm complexity. N choose k is very huge, especially n is very high and k also very high. So in this case, of course, this is p. So p choose k is very high, which means you need to compare a lot of candidates to find the subset k. So this is why many people already know this greedy approach is not the best, but still use the greedy algorithm. Because this is more convenient to compute, and also in practice, it provides you reasonably nice performance. Okay,